Good morning, everybody. I hope that you had a nice holiday. 1 month of vacation. Okay, so the topic of today's class is associative memories by attractors. I'll try and remind you the context. We started discussing it a month ago. So the idea is that we have a neural network that is characterized by some connectivity matrix between the neurons. And we are interested in structuring the network connectivity in some useful way. And the useful way is such that the fixed points of the dynamics that result from the connectivity matrix can be used for storing memories. So the idea is the following. So we have, this is a two-dimensional representation of the multidimensional space that characterizes the activity of the neurons in the network. And this space of possible states of the network is characterized by fixed points, denoted by these by the points. And the idea is that each of these fixed points corresponds to a memory pattern. Each of these fixed points corresponds to a different memory pattern, and around each of these fixed points there is a basin of attraction such that if we start from this point, we will converge to this fixed point, or if we start from this point, we will converge to this point. But if we start from this initial condition, from this point, the dynamics would converge to a different fixed point. And this is the idea of associative. In some sense, this is related to the or should model the idea of associative memory, in the sense that we provide the network with partial information about the memory pattern that we are interested in, and the dynamics converge to the exact memory pattern. We provide partial information, but the dynamics of the network converges to the full memory pattern that was encoded in the network. So all these idea is that these memory patterns are attractors. Now, there are several things that we are interested in. One is that we will be able to store multiple patterns in the network. Memory, where we already discussed the bistable in months ago when we talked about the dynamics of neural networks. We considered the situation where the dynamics is bistable. So a bistable system can encode one memory pattern. So we are interested in something more interesting. So we would be interested in structuring the connectivity such that there will be many attractors. This is one requirement. Second requirement is that these attractors would correspond to memory patterns, and not all patterns would be attractors. Remember, we discussed the possibility that each neuron is connected to itself, and then basically we have a 2 to the n fixed points, or 2 to the n stable fixed point, 2 to the n attractors in the network, but then we lose this associative or pattern completion property that we will be interested in. So we don't want, the goal is not to have as many attractors as possible. The goal is to structure the network such that the existing attractors are of interest, are those that correspond to a memory pattern. That's one requirement, or several requirements. And another requirement is that we are looking for a method of structuring the network dynamics in a biologically plausible way. We would be interested in understanding how these requirements of the associative memory that I discussed emerge from synaptic plasticity rules that have some biological plausibility. And the model that we will discuss that has these properties is known as the Hopfield model. We will be discussing a model that is known as the Hopfield model for associative memories, and I will define or describe the model, and then we will spend the next 4 hours studying its properties. So I will give 4 hours today. Those that missed run will have to wait another week. The last hour would be kind of an exercise. So I will take Ran's place. So the model is described in the following way. First, we describe the dynamics of neurons in this network, and we will use the standard rate equations that we discussed a few weeks ago. So SI dot, the activity of neuron I, the change in time of the activity of neuron I as a function of time, is equal to minus SI plus some sigmoidal function G of HI. There's something missing here. Tau, units, yeah, tau. I should add tau here, but we will measure time in units of the characteristic time of the neuron. So it's like assuming the tau is equal to 1. The sigmoidal function that we will use, g of x, is hyperbolic tangent of beta x. The input to the neuron, HI, would be equal to sum over J of Jij Sj, sum of the activity of all neurons in the network weighted by the synaptic connectivity strength. And we'll make another assumption that we will consider very large networks. How many neurons do we have in the brain? 86 billion, yes. Well, I don't know about the 6 or even not the 80. Something like 10 to the 11. 86 is good enough. Well, 86 billion. So networks are large. Well, this is our brain, at least my brain. If we talk about other animals, it could be 1 or 2 orders or even 3 orders of magnitude smaller, but still these are very large numbers. It's true that not all neurons in the brain are associated with memory, but thinking about cortical networks, it's definitely in the order of millions and more. So this assumption of a large network is justified, and then if we'd be interested, we can or actually we will study how the properties of this network change with a number of neurons. The next assumption, okay, so this defines the dynamics of a network. The next thing that we will do is discuss these memory patterns. These are the required fixed points of the network. And we will define memory patterns. So what's a memory pattern? Memory pattern is a vector that describes how each and every one of the neurons in the network, or that describe the activity of each and every one of the neurons in the network. So we will define it in the following way. So we will denote it by the letter P. So P mu, this is the memory pattern number mu, is a vector of length n, P1 to Pn mu, where Pi mu is plus minus 1 with probability half. Let me try and explain it again. So in principle, we could have required. So I started by telling you that we would like a model that dynamic model whose dynamics is such that the fixed points are memory patterns. So memory patterns correspond to one way of thinking about it is, let's say that I'm presenting you with this picture. This picture elicits some pattern of activity in your brain, somewhere in your brain. Now, I instruct you to memorize this picture. Now you close your eyes, and I'm instructing you to try and memorize and recall. I'm instructing you to recall this picture. What I would like is that the neurons in your brain, that the activity of the neurons in the brain would reproduce this picture, or in some region in the brain that functions, or whose function is to memorize and recall this picture. As a result of the instruction, please recall this picture, the pattern of activity of the neurons would be similar as possible to the pattern of activity when you view this picture. Now, this requirement tells us something about the properties of pictures in the world. So, what I'm assuming in this model, that memory patterns have this property that, on average, half of the neurons are active and half of the neurons are inactive, and that, and I didn't write it here, and that the activity of different neurons and of different neurons for the same pattern and for the same neuron in different patterns is independent. In other words, this is a property of the world, at least the world as this brain region that is associated with the memory sees it. Okay, so I'm assuming that the memory patterns that will be encoded in this network have this property that the activity of the neurons is either plus or minus 1 with some probability 1/2. Yes? Right. Actually, it cannot be plus and minus 1. These neurons, well, when beta is finite, the neurons cannot be plus and minus 1. This is a requirement. That's a memory pattern. Maybe I will fail. Maybe the activity of the neurons would be this multiplied by 0.99999. And then, we're almost there. Then we would say that the model is good. But if eventually these fixed points would be such that all neurons, the activity of all neurons is 0, then this would correspond to a complete failure. But you are right that these neurons cannot, as long as beta is finite, cannot reproduce or this pattern of memory. But maybe they can reproduce something that would be close to it. Any more questions? Now, this requirement, it's a rather strong requirement and not very, in many sense, in some sense, not very plausible. It's not very plausible, for example, because if I have some topographic representation of this picture, 2 points in this picture will have a similar representation because of correlations in the spatial correlations in this picture. So saying that the activity of the different neurons that correspond to the activity of, let's say, nearby neurons in the network is uncorrelated is a strong requirement. But I would like to go back to this point later because there are solutions. And we can go back to this, to the plausibility of this assumption later on. Any more questions? Yes. No, I'm not saying anything about the neurons themselves. And finally, and this is perhaps the most interesting part, I'm assuming that Jij, the connectivity matrix between neuron I and neuron J, is equal to 1 over n sum over mu of pi mu pj mu. And this is for I that is not equal to j, and jii is equal to 0. So let's see what this means. This is easy. This means that neurons are not connected to themselves. Okay. Let's look about this. Let's think about this this statement about the connectivity matrix in a framework of learning. So the way to think about it is the following way. I'm taking my brain region, I'm presenting this picture, and I get some activation of neurons in the brain. I start with my initial connectivity is very weak. So there are very few connections in the brain. I present pattern number 1, and after presenting pattern number 1, okay, so let's write it here. So I present pattern number 1. And I make changes to the connectivity between neuron I and neuron J to be equal to 1 over n, the product of the pattern of activity the product of activity of neuron I and neuron J. So I start with a network whose connections are very weak, maybe 0, I force this pattern of activity into my neurons. This is by looking at the picture. And as a result of this pattern of, as a result of this activity, I have changes in the connectivity between neuron I and neuron J, such that the change in the synaptic connectivity between these two neurons is equal to 1 over n. This is just a parameter times the product of presynaptic activity and postsynaptic activity. Now I present another pattern. This would be looking at a different picture. I'm looking now at the picture over there. This picture over there generates a different pattern of activity in the brain. And now I'm making another change in the connectivity between neuron I and neuron J to be equal, again, to this prefactor 1 over n times the activity of the neuron, times the product of activity of neuron I and neuron J when looking at this picture. And I'm going to pattern number 3, pattern number 4, pattern number 5, and so on, until I go over all the patterns that I want to learn, all these beautiful pictures on the wall. And finally, what the resultant connectivity would be equal to this prefactor 1 over n times the sum over all memories or memory patterns that I encode in the system, sum over all these patterns, where each pattern contributes the product of pre- and postsynaptic activity corresponding to this pattern.
When you are averaging their connectivity?
I'm not averaging, I'm summing.
Yeah, or over, you divide by n.
N is not the number of patterns, n is the number of neurons.
All right, so you're summing but along the different patterns.
Yes, every different pattern would correspond to different activity of the neurons, and this would correspond to a different contribution to the connectivity matrix. Yes.
So this is something you do to kind of preset the system. It's not biological, right? You go through all the memory patterns.
Well, okay. So this is the answer to your first question is yes. This is something that I preset. Now the question: is it biological? So I would like to argue that it is biological in some sense. It is biological in the sense that first, well, when we learn things, we learn them in a sequential way. So I learn this, then I learn this, then I learn this, then I learn this. I don't do it all at once. And this is something that is achieved using this algorithm. So in other words, the resultant connectivity matrix can be understood as resulting from a sequential learning. We will not talk much in this course about sequential learning. This would be more, you learn more about it with Yoram in next year. But the point that I'm trying to make is that this sum over memory patterns can be understood as resulting from a sequential learning process. This is one aspect of the biological plausibility. The second aspect of the biological plausibility is that the synapse between neuron I and neuron J, so we have neuron I and we have neuron J, and they are connected. So the synapse between neuron I and changes to the synapse Jij are a function of information that is available to the synapse. It's information about activity inside I in the presynaptic side and the postsynaptic side. So when this synapse changes, the only information that is required for this change is information that is available to the synapse. Remember, synapse is just is a property of the pre- and postsynaptic neuron. So in principle, synapse knows what's going on in the presynaptic neuron, and it knows what's going on in the postsynaptic neuron. It doesn't know what's going on in other neurons. And this learning rule, or this rule that determines how synapses change, requires that the synapse would have information only about the presynaptic side and the postsynaptic side. So in that sense, it's a plausible learning rule. This rule is known as Hebbian learning rule. And there is quite a lot of evidence that synaptic plasticity rules in which changes are a property of the product of pre- and postsynaptic activity, there's quite a lot of biological evidence for this kind of synaptic plasticity rules. Not the details, but in general.
But in a way, you need to have the memory already stored before you can do this. I mean, P1 needs to be P1, right? And then only then you can teach the...
Well, I cannot learn something that I don't know anything about. I have to get some information. So, I'm looking at this picture. All my brain is now changing in response to the visual stimulus coming from this picture. It is so important. I remember everything. And now it's in my brain. But I needed this viewing episode, or I needed this input at least once so that I'll be able to remember. You can't remember things that never happened. Well, maybe you can, but we'll discuss it later. Yes?
I don't understand. Since you force the key I all be either 1 or -1, but none of it will be 0, you're going to get a very high connectivity, right? Which is a lot more than what actually is in the brain, because you're basically physically connecting all your neurons together.
Okay, so the issue is you're asking a question. Let's take, I will rephrase your question. You're saying the following: Jonathan, let's take what you're saying seriously. In every pattern, half of the neurons would be active. And I'm looking at this learning rule, and I conclude that the connectivity in the brain should be all-to-all, or almost all-to-all. And I'm an expert in anatomy, brain anatomy, and I know that this is not the case. So why continue, right? That would be well. It's even. I'm sorry. Well, you're expert enough to notice that there's a problem here, but I will tell you that there are other problems. For example, doesn't seem that the patterns are plus and minus 1 with a probability 1/2. Even active and inactive with a probability 1/2. Half, when we look at memory patterns, it's much sparser.
Yeah, the reason why that specifically bothers me is because it's raising the dimensionality of the system. That's very expensive.
Well, at this point in time, I would like to ignore your question and say that I'm not going to deal with it. And the reason is that it will be very useful for the calculations that we will make to make this assumption. And one nice property about this model is that it's very robust in the sense that now you can kill 90% of the connections, make them in the model, make them equal to 0, and still many of the properties remain. So for this assumption that we will make is for mathematical convenience, as well as this assumption, and hopefully towards the end of this day, we will go back to the biological assumption and ask the question: how do we relate this very abstract model to what we actually see in the brain? Yes?
You just said we can kill at least 90% of the connections. That means that Jij, at least 90% of them could be zero. It still would have the same, what is the membrane pattern?
No, it will not be this. Let's leave.
Good enough.
It will be easier for me to answer this question after we understand what's going on before killing them. So let's leave this question to later today. Okay, so this is the model. Now, before doing anything with this model, I would like to make sure that all of you understand the model. So what do I mean by understand the model? It means that you are able to simulate it. Maybe doing the calculations is complicated, but I would like to make sure before we go on that you all understand it in the sense that you can write a MATLAB code that will do this. And because if you can't do it, then it means that you don't understand the model. You don't understand our initial point. So is it clear to everybody? Okay. So we will start just to gain insight. We will consider a simplified case. And this simplified case would be take the limit of beta goes to infinity. For those physicists in the audience, beta can be it's not a coincidence that we're using beta. This is can be understood as 1 over temperature in a stochastic version of the model, but for the purpose of this course, beta is just a parameter. So we will start with a simplified case where we will take the limit of beta to go to infinity. And the question that we will ask ourselves is, given this connectivity, are these memory patterns? Are the memory patterns fixed points of the dynamics? So let's try and understand it again. So we have these memory patterns. We use these memory patterns to learn the connectivity matrix. And the question that we ask ourselves is, okay, now we have this connectivity matrix. Will these memory patterns, the ones that were used for learning the connectivity matrix, are these memory patterns fixed points of the dynamics? That's our question. So what's the condition? What is the condition that these memory patterns would be fixed points? What's a necessary condition? Necessary and sufficient. Well, I didn't even require it to be stable. So you're asking something that is too strong, because I didn't say stable fixed points. I mean, if they are not stable, it's not very interesting, but I'm starting with a simpler requirement that it would be a fixed point. What's the meaning of a fixed point? So the idea is that if I start with these initial conditions, I will stay there. Okay, so what's a fixed point of this equation? Si is equal to GHI. That's a fixed point equation for each of the neurons. What's G of HI in the limit of beta goes to infinity? Sine. So the requirement basically is that Si, the fixed point equation for this equation, the fixed point equation for neuron I in the limit of beta goes to infinity is Si is equal to the sine of Hi. That's the fixed point equation, taking this equation and the limit of beta goes to infinity. Now, in order for a memory pattern to be a fixed point, the requirement is that pi mu, in order for memory pattern to be a fixed point, the requirement is that pi mu is equal to sine of sum over j of jij pj mu. And this has to be true for every I. If this is true for every neuron, if for every neuron, if all neurons in the network are in memory pattern mu, then the fixed point equation holds. Then we know that a pattern mu is a fixed point of the dynamics. Is this okay? Are you happy with this equation? Questions? What's the time? Rewriting this equation, basically what we need is that the product of pi mu times sum over j of jij pj mu should be what? Any suggestions? Choose a number between minus infinity and infinity. What's the requirement for this product? It has to be positive. Doesn't have to be equal to 1 because this is not equal. All we care about is the sign of this term, not about its exact value. So this is the requirement. And this has to be true for every neuron. This is in order for us to prove that pattern mu is a stable fixed point. So the next step would be to check whether this is indeed true. And I will do it for pattern number 1. I will consider the case of mu which is equal to 1. Doesn't matter, just it will be simpler with respect to the notations. So what we are doing now is we are checking whether this equation holds. So how do we do it? Well, I'm looking at the product of pi1 times sum over j of jij pj1 and this is equal to pi1 sum over j is not equal to 1, 1 over n, sum over mu, which is equal to 1 to p, pi mu, pj mu times pj1. So what did I do here? Two things. First, I took this jij term and substituted this term. This is capital P. And second, note that this is only true for the case of I which is not equal to j, and because in our model jii is equal to 0. Which reminds me that I forgot to say something important. How do we know at all that there are fixed points in the dynamics? We already know, we can already know that this dynamics that we are studying will converge to a fixed point. How do we know that? Yes. So we worked hard 6 weeks ago or so to prove that that this dynamics, for the case of a symmetrical network, this dynamics converges to a fixed point. We did it by introducing the Lyapunov function, a particular Lyapunov function. Now note that this connectivity matrix that we are postulating is symmetrical. Jij is equal to jji. So we are sure that the dynamics would converge to a fixed point, but now the question is, what fixed point? Is it a fixed point that we are interested in? What would be the next step? Here the students that took the course in computation and cognition have some advantage. And so the next step is to take this sum and separate it into 2 parts. One is where mu is equal to 1, and one when mu is not equal to 1. Okay, let's do it. And then we will understand why I'm doing it. So this will be equal to pi1 times sum over j is not equal to I. 1 over n times pi1 pj1 times pj1 plus, I will reorder it, 1 over n, sum over mu is equal to 2, from 2, is equal to, goes from 2 to p, of pi1 pi mu, sum over j is not equal to I, pj1, pj mu, pj1. So let's see what I did here. I just took this sum and separated it into terms where mu is equal to 1 and terms where mu is not equal to 1. This is one thing that I did. So I have these two sums. And another thing is I just reordered things. I took the sum outside. I took 1 over n outside and reordered the terms here. And why did I do it? Well, I did it because what's the product of pj1, pj1? 1. Why 0? We said that pi mu is 1 or minus 1. So it can either be 1 or minus 1. The product is always equal to 1. So this is equal to 1. And actually we can take the pi1 outside the sum because the sum is over j. Let's rewrite this. I apologize. We can just change the order of terms here. So this product is equal to 1. This product is equal to 1. So this term is equal to what? Almost 1. It's equal to n minus 1 over n. Why n minus 1 and not n? Yeah, because we don't take we sum over n minus 1 terms. N minus 1 terms. What can we say about this term? What is it equal to?
If P is large, you could use the assumption about the probability. If half of the patterns are with the same sign as PI1 and the other half the opposite sign. You can try and divide it.
So we cannot give a definite answer. Why can't we give a definite answer? Because we don't know what these pi mu are. So we cannot give a definite answer to the question of what is this term. All we can say, perhaps, is something statistical about this term. We can say something about the distribution of this term, because we know something about the distribution of these pi mu. And we can do it both for p that is small, np that is large, n that is small, n that is large. We can do it for, given that we know the distribution of these terms, we can say something about the distribution of the product. Given that n and p are, given that n is large, you may be able to use the central limit theorem to say something more intelligent about the distribution of this term. But we cannot, this is not a deterministic term. This term is determined by the distribution, by the realization of the particular patterns. In other words, this term will be different if I view these pictures that are on this wall, or I view or try to memorize other pictures. So the value of this term would be determined by the exact patterns that I'm using, but maybe we'll be able to say something about the distribution of this term, and this we would do after the break.
שאפשר להתגבר עליו, זה הדברים שאתה אמרת.
אני חושב שזה רעיון יותר טוב לדבר על מה אפשר להתגבר, מה החולשות החוזקים של המודל הזה, אחרי שאנחנו נבין אותו. אבל כן, אתה צודק, המוח הוא לא, הקשרים לא סימטריים. מה שאנחנו בעצם נראה, מה שאנחנו נלמד מהמודל הזה, זה יהיה דוגמה לאיך אפשר לשמור זיכרונות בצורה מבוזרת. זה מה שאנחנו נדגים באמצעות המודל. עכשיו, זה מעורר שאלות שהן על גבול הפילוסופיה של מה בעצם אנחנו רוצים ממודלים. נגיד, אתה יכול, בכל הנחה מההנחות שהנחנו כאן, כל הנחת הדינמיקה, אם אתה תיקח מדידות מדויקות, תראה שההנחה הזאת לא מתקיימת. הכל פשוט. יש כאן איזה מסר שהוא מסר אידיאולוגי עמוק, שאומר את הדבר הבא. נניח שאני אצליח, שיש לי איזושהי תכונות שאני אלמד מהמודל הזה שאני יכול לפתור אותם. אני מאמין אני אוכל גם לבדוק באמצעות סימולציות, שאם אני מתחיל לשנות, שאם אני משנה בצורה לא נורא משמעותית, ואולי אפילו גם כן משמעותית, אם אני משנה את אם אני מסבך את המודל הזה, עדיין האסנס יישאר. והאסנס שעליו אני מדבר זה הרעיון שיש לך אטרקטורים, שהדינמיקה יוצרת אטרקטורים, ושהאטרקטורים האלה מייצגים תבניות זיכרון, ושיש לי דרך ללמוד את תבניות הזיכרון האלה באמצעות חוקי למידה לוקליים, שמשנים את ה-connectivity matrix ומשנים את האטרקטורים. זה הלב של המודל. ובעצם, נסתכל על זה בשלב הזה, על proof of principle. יש המון עבודות בספרות. אני יכול להעביר קורס שלם בנושא של אתה מתחיל לסבך את המודל ואתה רואה מה נשמר ומה הולך לאימון. וקצת אנחנו נדבר על זה בסוף. וכל הנקודות האלה, תעלו אותם, ואז נוכל לדון ספציפית מה קורה ככה, מה קורה שחורגים 90% מהקשרים, כל הדברים האלה. אז לחלקם יש תשובה קלה ולחלקם יש תשובה לא קלה.
אם המדברים עדיין רציתי לשחק.
כן.
המעבדה בפיזיקה, יש לה יכולת לשחק עם מעגלים צמודים. אני שואל אותך, אם יש לך רעיון להדגמה, או ניסיון להדגמה, מעניין שאפשר לעשות עם מספר קטן של מעגלים, בהקשר של רשת. אם אפשר לנסות, לא יודע, מה שחשבתי, רעיון ראשוני מאוד, זה נגיד 4 מעגלים צמודים, ולראות אם אני יכול בטווחים, להגדיר טווחים של תדר מאלץ, שבכל טווח אני רואה איזה פעילות יש להם ביחד. זאת אומרת שאני יכול להגיד שהם יודעים לסווג לעצמם על כל מיני טווחים של תדרים, איך הם מסתנכרנים, או משהו כזה.
יש גם עבודות אנליטיות או דברים דומים.
אם יש דברים אנליטיים שאני יכול לקחת ללמד במעבדה, זה נהדר.
השאלה היא, קודם כל, צמדים זה יותר מורכב. יש שאלה שאתה לוקח איזשהו אוסילטור, אתה אינפורסית, וזה אינפוט שהוא תדר קצת אחר. אוקיי, שאתה לוקח אוסילטור, ונדרפול אוסילטור או משהו כזה.
אוקיי.
אתה מכניס לו אינפוט אינפיניטסימלי חלש, וזה תדר שהוא לא התדר של אוסילטור. לא תהיה שום השפעה. אם אתה מכניס אינפוט שהוא אינפוט חזק, אז it will entrain האוסילטור. כדי שהאוסילטור שלך ינוע בתדר החדש, לא בתדר החדש.
העניין הוא שאני צריך לשכנע את המדריך במעבדה, הנושא של המעבדה זה מעגלים מוצמדים.
אוקיי.
במעבדה יש נושא, עושים כמה דברים פשוטים ואז עוברים להרחבה. עכשיו, מה שרוצים לעשות זה סך הכל שאני משחק עם מעגלים מוצמדים כמו מטוטלות מצוות, וזה קצת בנאלי, רציתי לעשות אולי, מה שהצעתי למדריך, הוא אמר לחזור אליו, זה לייצר להרחבה יותר משמעותית, ואז יותר יותר זמן לעשות את זה. ומה שאני רוצה לעשות זה להתעסק
במעבדה, זאת אומרת מעבדה זה נקרא, אני רוצה לקחת לי קצה, זה אומר אלקטרוניקה, שזה אומר
סימולציות, מעבדה ב' זה נותנים לנו לשחק בסיפור.
זה מה שקורה לי, אני כל הזמן כולה. יפה. ישראל. לא, אני אומר,
Okay, so we are studying the Hopfield model for associative memory. We start with a simplified case in which we take the beta, we take the limit of beta goes to infinity. We present, and the question that we ask is whether a memory pattern number 1, without loss of generality, is it a fixed point? I'm not asking whether it's a stable fixed point, I'm just asking whether it's a fixed point of the dynamics. And in order to, the condition for it to be a fixed point is that this would be true for every neuron. Rewriting this condition, we end up with this term, and we require, this should be true, we require that this would be positive, and we ended the last hour by understanding that this we can compute. This is just equal to 1 minus 1 over n. That's easy. But we have this term. And this term depends on the particular realization of the memory patterns. Different memory patterns will result in different values of this term. And so the question that we should ask ourselves is not whether memory pattern number 1 is stable, rather it is what is the probability that memory pattern number 1 is stable. And when I'm saying probability, I mean probability over the realization fixed. Everything is fixed. I'm not saying I lied. We're just talking, at this point, we're just talking about fixed point, not stable. And so we can ask ourselves, what's the probability that memory pattern number 1 would be stable? And the probability that memory pattern number 1 will be stable is equal to the probability that this term would be positive. It says stable again, right? I don't know. I apologize. So the question was, we can answer what's the probability that the memory pattern will be a fixed point. Actually, it will be stable, but I'm not proving it. So we're asking the question, what's the probability? So the probability that memory pattern number 1 is a fixed point is equal to the probability that this term is positive. And when I'm saying probability, it's probability over the realization of memory patterns. Am I clear? Yes. This is just going from here to here.
When it's positive, so it's bounded from below, then it's stable.
Stable, if you want to prove stability, you need to add perturbations. We're not doing it. We're just talking about existence, although it's stable. Okay? So this is the question. So let's look at this term. Let's see what we have here. How many terms do we have here? So this is a sum over p minus 1 element, and we have a sum over n minus 1 element. So the number of elements here is p minus 1 times n minus 1. What's the value of these elements? What are they equal to? It's 1, plus 1 or minus 1. Why is it plus 1 or minus 1? Because pi mu, pi1, pj mu, pj1 are all plus or minus 1. So the product is plus or minus 1. So I can write it as equal to n minus 1 over n plus 1 over n sum over k. K goes from 1 to n minus 1 times p minus 1 zk, where zk is equal to plus minus 1 with probability half. Why is it with probability half? Well, all these elements are plus minus 1 with the probability half. So the product will be plus or minus 1 with the probability half. And note that all these elements are independent from each other. Because we assume that the memory patterns are, that the activity of neurons within a memory pattern and between memory patterns is independent. So basically what we have here is a sum of n minus 1 times p minus 1 elements that are plus or minus 1 with the probability half. All these elements being IID distributed. So what's the probability that this term would be indeed positive? What's the next step? Any questions about this? So what's the next step? Do you all understand the question? We need to compute the probability that this term, is positive. How do we do that? You had a suggestion previously. You said something about central limit theorem, if I remember. Okay, I said. So we assume that the number of elements is large. N is large. So this term, n minus 1 times p minus 1, would be large. So we have a sum of a large number of elements that are all plus or minus 1 with a probability 1/2, and are independently distributed. So in this limit, this term, the distribution of this term becomes Gaussian. So this term that I will denote by just write it. So pi 1 times sum over j of jij pj 1 is normally distributed with some mean mu and standard deviation sigma square. So this is just from the central limit theorem. So the next step would be to compute mu and sigma squared. So how do we do that? How do we compute mu? I'm sorry? Which is, well, not, well, we have this term. The whole thing is equal to n minus 1 divided by n, plus average, and for reasons that I will not go into, averaging over realization of patterns is denoted by this double bracket term, 1 over n n minus 1 times p minus 1 divided by n times the average of this z term. What's the average of the z term? 0. So this is just equal to n minus 1 divided by n, which is approximately equal to 1. Questions about that? How do we compute the standard deviation or the variance? Yes. Well, these brackets, this is a notation telling me that I'm averaging over the realization of memory patterns. In some models that we will not discuss, we also have a stochasticity in the dynamics of the neurons, and this is the standard notation is one bracket, and for stochasticity in the dynamics, and the standard notation is double bracket for the stochasticity in the realization of patterns. So this is just a notation. Okay, so what do we need to do next? We need to compute this term. So how do we do that? So basically you gave us the answer, and you're absolutely right. So the variance, so we're talking about the variance of this term, because the mean of this term is equal to 0, and we're talking about the variance of this term, and this is equal to 1 over n squared times the number of elements here, n minus 1 times p minus 1, times the variance of the individual term, which is equal to 1. So taken together, sigma squared is equal to n minus 1 p minus 1 divided by n squared. And assuming that both p and n are large, this is approximately equal to p over n. So those of you who have a hard time computing this term or understanding how this variance was computed are invited to ask Ran for an extra hour on how to do these things. Yes?
Are there any limitations on the value of p, considering the number of n?
So far, no. I'm asking the question, what's the probability? What's the probability that there will be a mistake?
No, not generally discussing in this model. Is there a limit to how much the network can remember?
The answer is yes and no. Well, yes, there is a limit to how much the network can remember, and we will compute this limit, or an approximation to this limit. The actual computation of the limit goes beyond the scope of this course. We will do an approximation. So what's the probability of a mistake? Me. What I mean is, what's the probability that for a particular neuron, the condition for a fixed point would not exist? So we're asking the question, what's the probability that the fixed point condition will not hold for a particular neuron I? Well, perhaps excuse me for interrupting you. Let's say that there was only one memory, and this goes to your point. Let's say that for the sake of argument that there is only one memory pattern in the network. We embedded only a single memory pattern in the network. What's the probability that the fixed point condition will not hold? 0, very small. Any other suggestions? Half. Well, what's the variance? Well, it's not close to 0. Actually, it's exactly 0. Well, this was after the approximation. So the way to think about it is the following, okay? So we have this, let's call this term, X. So what I'm plotting here is the distribution of X. So this is the probability, and this is X. So what I'm plotting here is the probability distribution of X. Probability distribution over what? Realizations of memory patterns. Probability over the realizations of memory patterns. What's this value here? 1. What's the width? So the width is approximately a square root of p over n. So what's the probability that a fixed point condition will not hold? This is the area where? That's the probability that X would be smaller than 0, and this is the area under this Gaussian the negative part of this Gaussian. So one thing that you can immediately see is that this area depends on the number of memory patterns that we encoded in our network. The larger the number of memory patterns we encoded in our network, the larger is the probability of a mistake. I'm sorry, probability that a fixed point condition will not hold. So we expect that we expect that if P is sufficiently large, or P over N, I'm sorry, if P is sufficiently small, or more precisely, if P over N is sufficiently small, then the probability that the fixed point condition will not hold will be negligible. And what we will do now, we will be slightly more precise about it. Yes. The reason that I'm calling it a mistake is the way that I'm thinking about it is that you it's a measure of a mistake. It's not an exact thing. But let's think about what will happen. Let's say that that the fixed point condition holds for all neurons except one neuron. We present the initial condition of the network are memory pattern number 1, and the fixed point condition holds for all neurons except for one neuron. So what will happen is that after a short period of time, characteristic by tau, the time scale of the network, all neurons in the network will correctly encode the memory pattern except one neuron. Or the memory pattern, or the spatial pattern of activity in the network will be correct for all neurons except one. So you can think about this one as a mistake. Now, what will be the consequences of having this mistake is slightly complicated. It can end there, or maybe the fact that you have a mistake in neuron number 1 would result in change now in the activity of neuron number 7, so we'll have 2, and maybe this would result in a third neuron being inaccurate, and so on, and then everything fails, or maybe it will stop there. So it's complicated. That's why I'm calling it a mistake. So the next step would be to compute the area here. So what we will do now is compute the area here. And so what would be the area here? Let's say. So this is a notation of saying that for neuron number I, the value of x is negative. So what we're doing here is we're trying to compute this probability. So what's the integral that describes this area? Of the Gaussian. Which can be simply written as an integral from minus infinity to minus 1 over sigma by changing variables. I'm sorry? You can call it. This is just a. It's a. I don't know, משתנה אינטגרציה. Integration variable? What's it?
But you don't mean the Z from there?
I'm going over. Yeah, we can. You can call it x. Doesn't matter. It's just an integration variable. So basically, what we are doing is we are computing the area here. Now, this is a probability of a mistake. Sorry. This is a probability that the fixed point condition does not hold for a particular neuron number I. But remember that we will be more strict, and we would require that the stability condition would hold not just for neuron I. This should be true for all neurons. This should be true for all neurons in the network. And there are many, many such neurons. So we will be interested in a regime where this term is small, where this area is small. In other words, we will study this integral in a regime where sigma where sigma is very small. We will study this integral in a regime where sigma is very small. And now what we will do a short mathematical detour in which we will learn how to estimate the area of this integral in the limit of sigma that is very small. It's a very useful approximation. That's why I will spend some time on this mathematical detail. So how do we do it? Any suggestions? Did you learn it in any of the mathematical classes? No, right? I'm sorry? It's not a bound. We will approximate this integral. How do we approach it? So our integral is the integral from minus infinity to minus 1 over sigma dz e to the minus z squared over 2. So what we are going to do, an integration by parts. We will write it as an integral from minus infinity to minus 1 over sigma of 1 over z times z e to the minus z squared over 2 dz. And we will use the method of integration by parts. I'm going to call this u, and I'm going to call this v prime. Or maybe before that, what would be the naive approach here? If you have an integral from minus infinity to minus 1 over sigma, and I'm asking you to estimate it in the limit of sigma goes to 0, how would you do that? What would be the naive approach? What would be the value of the integral when sigma is equal to 0? 0. So you can do a Taylor expansion and use a Taylor expansion to estimate the integral. It doesn't work here because all terms in the Taylor expansion turn out to be equal to 0. So we need to do something slightly more sophisticated. So we are doing integration by parts here. So let's look at the value of v. V is an integral of z e to the minus z squared over 2 dz. How do we integrate this term? Sorry? Change of variables? No. What variable? What change of variables? K is equal to z squared divided by 2. So this would be equal to e to the minus k dk, because z dz is equal to dk. which is equal to minus e to the minus k, which is equal to minus e to the minus z squared divided by 2. So our integral, this integral that we're interested in computing, is equal to uv, which is minus 1 over z e to the minus z squared over 2 in the limit minus infinity to minus 1 over sigma. This is the first term. Minus an integral from minus infinity to minus 1 over sigma of, we take u prime, which is minus 1 over z squared times v, which would be minus e to the minus z squared divided by 2 dz. So this would be just uv, and this would be v prime u, which is equal to, this term contributes sigma times e to the minus 1 over 2 sigma squared minus an integral from minus infinity to minus 1 over sigma of one over z square e to the minus z square over 2 dz. So far, so good? So what would be the next step? Perhaps before going to the next step, I'd like to ask you a question. Which integral is larger? This one or this one? Which integral do you think is larger? This one or this one? The top is larger. Why is it larger? Because here I have the 1 over z squared, and z squared corresponds to terms that are larger than 1 over sigma. Actually, this one would be larger than 1 over, it will be larger than sigma squared times the previous integral. In other words, this would be a sigma squared correction to this integral. Another way of seeing it would be, so what would be the next step here to compute this integral? Do the same thing all over again, yes. So let's look at this. So basically what we will have here is I'm replacing 1 over z squared with 1 over z cubed times z e to the minus z squared over 2. So what will I get? I'll have, so I'll do integration by part. So I'll get this exactly as before. I have this as v prime and this as u. So I'll have this term, but now rather than having 1 over z, I'll have 1 over z to the power of, choose a number between 0 and 5. This is u. So it will be 1 over the cube. So rather than having 1 over z, I'll have 1 over z cubed with e to the minus z squared over 2 minus an integral, and this time I'll have 1 over z to the power 4. And next time that I will do it, I'll have 1 over z to the 6 and so on. So in other words, what we've proven is that this integral that we're interested in, let's write it. Okay, I'll write it here. This integral is equal to sigma e to the minus 1 over 2 sigma squared times 1 plus corrections, which would be order sigma squared. And if you're interested in computing these corrections, you already know how to do that. Integration by part. And now you also understand why the Taylor expansion could not have worked, because of this term e to the minus 1 over 2 squared, where the Taylor expansion always gives you 0. So this is a very useful approximation and very useful method, and that's why I decided to devote this time to teach you this method. So now we have well, we worked hard, but now we know the value of this pi mu. So this is just equal to can I delete it? So in the limit of sigma goes to 0, pi mu is equal to 1 over square root of 2 pi times sigma e to the minus 1 over 2 sigma squared. So this is a probability. This is the probability that for a particular neuron I, the fixed point condition does not hold. What is the probability that the fixed point condition will not hold for at least one neuron in the network? What's the probability that the fixed point condition will not hold for at least one neuron in the network? So I'll denote it by P minus. P minus is the probability of at least one mistake. And this is equal to 1 minus Pi minus to the power of n. Why is it true? 1 minus Pi mu is the probability of no mistake in neuron I. 1 minus Pi mu minus to the power of n is the probability of no mistake in any of the neurons. 1 minus this term is the probability of mistake in at least one neuron. And this is equal to 1 minus e to the n log of 1 minus p minus I, which is approximately equal to 1 minus e to the minus n times p I minus, where I took where I assumed that p I minus is small, and I Taylor expanded the log term. Yes.
The probability for mistake was the probability for this term that you said to be larger than, to be smaller than 0, right? If you remember, you wrote
The area here.
yes, and this was because you wrote those 3 lines at the beginning. So the mean, they are not equivalent, right? This is just like a necessary for not mistake.
This was I'm computing the stability condition, and the probability for a stability condition to hold, the probability that the stability condition will not hold for neuron I is this area, denoted here as pi minus. And we computed it to be equal to this term. Okay, so what's the next step? So the requirement, so we already understand that the probability that the stability condition will not hold depends on the standard deviation, on sigma. We know that sigma depends on p. We know that the larger p is, the larger sigma is, the larger is the probability that the stability condition existence, not stability. I apologize. The fixed point condition, we know that the fixed point condition, the probability that the fixed point condition will hold increases as p decreases. The best would be p which is equal to 1. If p is equal to 1, we are sure that all neurons, that there will be, that stability condition will hold for all neurons. The larger p is, the smaller the probability is that the stability condition would hold for all for all neurons. And now the question is, let's say that I want that the probability, I want the fixed point condition to hold for all neurons with a probability that is at least 99%. What should I do? Or 99.9%. What do I need? How do I find the p such that this condition would hold? I'll repeat my question. What's the probability that the fixed point condition would hold for all neurons? Or what would be the maximal p? What would be the maximal number of memory patterns? What would be the maximal number of p such that the fixed point condition would hold for all neurons with a probability of 99%? So how do I do it?
99.9. On the other side, we just put all the terms until we have p on the right side.
So we can decide, for example, that well, basically this 99% maps into a condition on this term. So we have a condition that n our condition is that n times pi minus should be larger or smaller? Should be larger, should be smaller than some number that I'm going to denote as n. N is a number. It's a rather meaningless statement. N is a number, but what I mean here is that depending on how certain you want to be, whether you want to be certain with a probability of 99% or 95%, or perhaps 99.9%, there would be a different requirement for this term n times pi minus. There will be a different requirement which depend on the exact condition that you put here. But n would be order 1. So this is perhaps a more useful statement. Now, let's say that n is equal to 5. Or n is equal to 10. This would give you a different this will give you a different value for p minus. Yes.
Just to understand, this implies that increasing the number of neurons is not good, which doesn't make sense.
Well, you have to remember that n is also in sigma. Yes, you have n sigma. So before taking the break, we'll have some requirement on n times p I minus. It has to be smaller than some number. The exact value of this number depends on my condition, whether I want 95% confidence, 99% confidence, 99.9% confidence, but n will be order 1. 1, 2, 3, 4, 5. It doesn't scale with n. And what we will do after the break, we will consider the consequences and compute this probability. Any questions before the break?
התחלנו שאמרנו, אוקיי, מה התנאי שהווקטור, שהתמונה תהיה fixed point, אמרנו אוקיי, SI יהיה שווה
זה כתוב פה. זה צריך להיות גדול מ-0, זה צריך להיות מספר חיובי. כן, איך הגעת לזה? היה לך שורה ראשונה, שורה שנייה, שורה שלישית כזאת. זה התנאי שעשיתי. נכון, וזה בדיוק, התנאי שזה גדול מ-0 זה היה השורה השלישית גם. שהיא רק נבוא. מה השאלה?
לא, אני זוכר, התחלנו מהתנאי הראשון, זה
עשה נפלטים במסך, נדלקו לי, יש לי איזושהי תבנית שנדלקה, אבל בעצם, יש לי מניח הנוירונים, זה הנוירונים שאנחנו מדברים עליהם, יש פה איזושהי כמות של נוירונים. עכשיו, מראש התבנית בהינתן התמונה שדולק תלויה בקשרים הכביכול התחלתיים שיש.
לא, אתה מניח שהאינפוט החיצוני הוא override.
הוא כאילו, אוקיי, הוא כאילו קישור אחר שמדליק לי אותם מראש.
זה אינפוט חיצוני.
כן.
להביא מהריקליים קונקציה.
שזה הגיוני ביולוגית?
כן, שזה הולך בגן חיות או אציל, קשה לך יותר סטיילינג מאשר זברה שתתחר.
זה כאילו מניח שיטות, אתה אומר אוברייד, כאילו הקשרים ביניהם לפחות בהתחלה לפני שלמדתי את זה הם הרבה יותר חלשים מאשר
גם אחרי שלמדת, האינפוט החיצוני הוא דומיננטי האינפוט החיצוני הוא דומיננטי בתפיסה, זה הטענה. אולי הטענה הזאת היא באמת יותר חלשה ממה שהיא נשמעת. זאת אומרת, יותר יכול להיות שהיא לא נכונה ממה שזה נשמע. אבל כשאתה רואה אותי, אז הטענה היא שאתה מייצג בצורה פחות יותר מדויקת כבר למה שאני
כן, ואז אני נזכר.
אתה גם יכול לחשוב על זה ברמה של היררכיות, שיש לך היררכיות, לא שיש לך עולם חיצוני וזיכרון אחד, אלא שיש לך היררכיות. תודה.
דבר שנייה, SI זה המצב של נוירון I. זה יכול לתרגם את זה לוקטור הזה? זה המצב של נוירון I?
זה המצב של נוירון I, זה תבנית הרצויה, זה תבנית הזיכרון, משהו אחר. תבנית הזיכרון לא.
למה אני שואל? דעתה עד לפה זה בסדר מעולה, סף הדאטה שווה אינסטוף. אני יכול להציג במקום ה-HI ולקחת את זה לפה. מה שאתה עושה, אתה מצטרך את ה-F שמנסים.
אני שואל את השאלה, בהינתן שהכנסתי לרשת את תבנית הזיכרון T, האם היא נשארת את תבנית הזיכרון T? האם תבנית הזיכרון T ניתנת לדרישת הפיקס פוינט?
אוקיי, מה הקשר בין SI ו-T-Mu?
P-Mu זה תבנית הזיכרון P-I-Mu, זה הפעילות של נוירון I ותבנית הזיכרון Mu. עכשיו אני שואל את השאלה, נניח שאני כופה על הרשת את תבנית הזיכרון Mu. זאת אומרת, נוירון 1, פעילות שלו זה F1Mu, נוירון 2, פעילות שלו זה F2Mu, נוירון 5, פעילות שלו זה F5Mu. נניח שאני כופה את זה. האם משוואות הפיקס פוינט מתקיימות? אם הן מתקיימות, זה אומר שהרשת תישאר במצב הזה.
SI כאילו? זה כאילו SI זה כאילו SI כוכב?
זה תנאי התחלה. יכול להגיד לך, P-Mu תנאי התחלה. משמש כאן שני תפקידים. משמש אותי לבנות את מערכת הקשרים, ועכשיו הוא משמש אותי כתנאי התחלה של הרשת. אני בודק האם בתנאי התחלה האלה, האם תנאי התחלה האלה הם פיקס.
זה נעשה מעבר ל-F ו-T?
כן.
מה ההבדל בין feed forward network שהיה לנו בשלב ולעומת מה שעשית בכיתה שזה positive define זה על ה-J, נכון? זה מה שאנחנו דיברנו בשלב הבית היה לנו feed forward network.
אוקיי.
נכון, בכיתה מתי שלמדנו את החומר הזה התייחסת לא ל-feed forward כן, recurrent network. מה הפרופרטי של recurrent? מה ההבדלים ביניהם?
feed forward network בוודאי תתכנס לפיקס פוינט. זה משהו לזה וזה עושה לזה וזה עושה לזה ואין מקום זה לא משפיע חזרה. ב-recurrent אתה עושה משהו לזה והוא יכול להשפיע חזרה וזה משפיע חזרה וזה משפיע חזרה, אתה יכול לקבל התנהגויות הרבה יותר ראשיות. אפשר להוכיח שבמקרה של קשרים סימטריים אתה עדיין מקבל את התמונה הזאת של פיקס פוינט שיש לך בכל feed forward גם ב-recurrent. במידה מסוימת אתה יכול לחשוב על אם אתה לוקח יש דמיון, זה לא אותו דבר, יש דמיון בין כך רשת recurrent תבנה אותה כ-feed forward, אבל שבכל שלב הקשרים הם אותם קשרים. אוקיי? תוכל מתישהו לכוון את השעון הזה כבר?
כן, בסדר.
כי אין לי שעון וזה מאוד מפריע לי.
בסדר, זה שעון קיץ או...
אבל לא, זה 10 דקות זז, זה הכל. זה לא קיץ חורף.
מתקדם קדימה?
זה בסדר גמור.
לא, לא בסדר.
כן, זה עכשיו.
אולי שעון שלך לא בסדר.
השעון שלי לא בסדר?
או שזה לא זז עכשיו, אבל...
אולי זה בסדר. לא, זה עכשיו לא, זה מראה את ה... עכשיו זה מראה שזה אחת, שזה...
אתה יודע, מאחורה...
קודם כל חורף קיץ. קודם כל חורף קיץ. זה 10, עכשיו 11.
זה בסדר גמור.
לא,
זה מראה
קצת
את זה.
מראה, קצת, הוא באמצע, בין 10 ל-11, צודק.
קיצור.
לא לזיז לו?
לא, זה בגלל שריבוי... לא.
זה עניין של הזווית שלי.
הוא קצת בעייתי.
לא, אם אתה מסתכל על הקווים, אז הוא בסדר. אם אתה מסתכל על המספר, קצת...
הוא זז או לא זז?
לא יודע, יש פה מומחים לשעונים של...
תחליף אותו לשעון דיגיטלי.
שעון דיגיטלי, כן. זה שעון דיגיטלי.
כן, אולי נביא.
נעשה איזה, כן.
אני נעשה מבצע.
אז איך יכול להיות שבפיד פורמט נטוורק, בסימולציה שעשיתי, יכול להיות מצב שבו פיקס פוינט הוא לא רק אחד ומינוס אחד, אלא יכולים להיות גם משהו בין אחד ומינוס אחד.
למה שלא יהיה?
אבל אתה ציינת עכשיו שבפיד פורמט הם בסופו של דבר...
גם ברשת קוניקרנט זה לא יהיה אחד ממינוס אחד.
יש זה תלוי בבטא, אם בטא היה מאוד מאוד גדול, אז זה בטוח אחד ממינוס אחד. תודה.
נכון.
אתה רוצה שמה שזה יהיה 0.99 מ-0.99? למה אתה מסתכל על הדבר הזה? אתה רוצה שכל הביטוי הזה, אחד פחות אקספוננט.
זה הסיכוי שיהיה...
סיכוי שלפחות אחד שלא מצליח.
נכון, אני חושב שהסיכוי הזה יהיה קטן.
אתה לוקח כל הביטוי הזה, ואומר שהוא קטן לא יודע, מה שאתה רוצה. למה אתה מסתכל רק על זה? למה לא?
המקום היחיד שזה בכל מקרה הביטוי הזה...
אחר כך תשים את זה באחד אקספוננט, כי זה אתה רוצה שיהיה קטן מ-0.99. כאילו, זה.
אני אומר שזה צריך להיות קטן מאיזשהו מספר. לא הבנתי את השאלה.
לא, סתם, אני לא הייתי מסתכל על כל הביטוי הזה. עושה עליו את התנאי, ואז בודק.
זה יותר מסובך.
לא, אתה מעביר את זה, עושה לה.
אתה רוצה שהאקספוננט יהיה יותר קטן אתה יכול לעשות את זה. זה יצא יותר מסובך.
טוב.
תעשה את זה, תראה שזה יותר מסובך. למה זה יותר מסובך? למה? אולי יהיה יותר פשוט להבין את זה יותר מאוחר, אבל הביטוי שאתה מקבל הוא לא ביטוי כזה פשוט. יש לך לקבל משוואה סתומה, אתה מנסה לפתור אותה.
אבל אתה יכול לעשות.
כן, אבל אתה יכול לעשות מה מספר שצריך.
זה לא בעיה, אתה רוצה, תגיד לי איזה...
זה אחד פחות אקספוננט של זה.
נכון, אבל אני אומר שהמספר הזה יהיה לא כל כך חשוב. עם התנאי, אני אומר שהתנאי, הבדל בין תנאי של 95% ל-99% ל-99.9%, זה יהיה הבדל ב-n הזה, שה-n הזה יהיה בין 2 ל-5. זה לא הבדלים נורא גדולים בחצי של דברים שאנחנו מדברים עליהם אחרים. זה יהיה קטן מאיזשהו מספר. זה הטענה.
Okay, so let's remind ourselves where we are. So this is a probability. This is a probability of that a fixed point condition would not hold for a single neuron. This is the probability that a fixed point condition will not hold for at least one neuron. So we would like this number to be as small as possible, which means that we would like this n times 1 minus n times pi minus to be as small as possible. So I'm going to require that n times pi minus would be smaller than some number that I'm going to call 1 over small n. So what would be the value of n? The value of n will depend on the requirement of on p minus to be small. So I'm leaving you as an exercise just to see that you understand what's going on here. Let's say that you require that the probability of a mistake, the probability that the condition does not hold for at least one neuron would be smaller than 1%. What does it mean about n. And when you want it to be smaller than 0.1%, what does it mean? What does it mean for n? And because it's exponential here, the values of n that you will get will be order 1. Or in other words, our requirement is that pi minus would be smaller than 1 over n, small n times large n times the number of neurons in the network. Or in other words, defining alpha to be the fraction of memory patterns to the number of neurons in the network, the requirement is that square root of alpha divided by square root of 2 pi e to the minus 1 over 2 alpha should be smaller than 1 over n, small n times large n. This is the requirement. Now this is slightly complicated. So basically what we want, and this is what you want, Hagai, is to find the requirement for P. We know that there is a limit. There is a limit to the number of patterns we can encode in this network without so that the fixed point condition holds. But we don't know this limit. We want an answer that has some structure. P is smaller than something, and this something should have in it small n. This is a measure of our tolerance to event where the condition will not hold. It will have a large n, number of neurons in the network, and maybe it will have a pi and all kinds of things. But it's slightly complicated because we have alpha both here and here. That's why it's slightly complicated. So as a first step, what I'm going to do, well, you should already realize at this point of your training that this is a dominant term. This would dominate the capacity because the dependence on alpha here is exponential, whereas it is a square. We have a square root dependence on alpha here. But let's do it in a slightly more formal way. We can take this take this inequality and do some algebra, and eventually we end up with this requirement. And to save time, I'm not going to go over all the steps, but it's pretty straightforward. So the requirement is that alpha is smaller than 2 times log n minus half log 2 pi plus log n plus half of log alpha. That's the requirement. Still doesn't help us much because this is a requirement. This is alpha has to be smaller than something that has alpha in it. So now I'm going to make 2 arguments. Okay, I'm going to make 2 arguments. First, I'm going to argue that these 2 terms are negligible. We can throw them away. We don't care much about them. Why is it true? These 2 terms. Both of them are order 1. Well, here we have 2 pi, and here we have n, which was determined by our tolerance to the possibility that in some cases it will not work, but almost independently of what our tolerance measure, n is order 1. So n is order 1 and 2 pi is order 1. So this is a dominant term. So this would dominate, log n would dominate relative to these two terms. So we don't care much about these two terms. What about this term? And this term is a term that makes our life miserable. So I'm going to argue that it's negligible also. And what I'm going to do, I'm going to use there are various ways of thinking about it, but what I'm going to do is use a self-consistent argument in order to show that we don't care much about it. So I'm going to argue that to a good approximation, this means that alpha has to be smaller than 1 over 2 log n. So let's go back and look at this term. So if alpha is smaller than 2 log n, this means, just a second, this means that alpha is smaller than 1, right? If alpha is smaller than 1, then this term, log alpha, is negative, right? So if this term is negative, then it means that the requirement for alpha, this requirement for alpha is a bit too restrictive. We could take a slightly larger alpha, because this makes the denominator smaller. So this means that this whole term is larger. So this means that this requirement for alpha was slightly too restrictive. Now the question is, how restrictive was it? What is the contribution of this term relative to this term? Now this term is log n. This term would be log alpha, something like log of 1 over log n. Or, in other words, minus log minus this would be term of the order of log n. And log n, when n is large, is substantially smaller than log n. So the inaccuracy or the contribution of this term to the bound that we have is of the order of log n. So this actually should be something like alpha is smaller than 1 over log n minus something times log n, which is substantially smaller than log n. So in the limit where n goes to infinity, this is a dominant term. That's why we don't care about. That's why we don't care about this term. Yes. So we what we are looking for is a limit for p. So allow me to go one step, and then I'll go back to your question. So if this is true, this implies that p has to be smaller than n divided by 2 log n, right? Because alpha is p over n. So if alpha has to be smaller than 1 over 2 log n, it means that p has to be smaller than n divided by 2 log n. So the scaling of p is approximately the scaling of n. It's n divided by log n, but now I'm not sure that I understood your question. Yeah.
Then if you neglect log p, then p is n is much larger.
It's log n. It's log n large. In the limit, it's log n larger than p.
Log n plus log p, you cannot just write log n.
Let's reach. I can complicate this equation such that I will not be able to see the relation, and I think that you are going in that direction by separating it. I'm looking at alpha. Alpha is good enough. I mean, if I have a condition for alpha, then it's equivalent to a condition on p. So if p is small, then I don't have a problem. The problem is as p gets larger. I want to see how much. What's the limit on p that I can take? What's the largest p possible? Now, ignoring this term log alpha, I know that the largest p that I can take, or the largest alpha that I can take, is something like 1 over log n, 1 over 2 log n. Now, going back to this equation, I learn that actually I can take a slightly larger value for alpha, because if I substitute for alpha 1 over 2 log n here, I get a number that is slightly larger than this term is slightly larger, but the difference is on the order of log n. So this is negligible compared to log n. So this is cutting a long story short. It was a very long story. We know that if p is smaller than n divided by 2 log n, then with a high probability, there will be no mistake. Again, rephrasing it. So the fixed point condition would hold for all neurons in the fixed point condition would hold for all neurons in the network. Yes.
How this result is not dependent on the small n, because I couldn't show the small n to be appropriate in half.
It will be a correction here. So there will be a correction that will depend on small n, but it will be small, because in the limit of large n, this is the dominant term. Now you can ask a question. Okay, this is good. We know what's the condition that memory pattern number 1 is a fixed point with a high probability. But this is only true for memory pattern number 1. What is the condition that all memory patterns would be a fixed point? That the fixed point condition would hold not only for memory pattern number 1, but for all memory patterns. It's more difficult, right? Here we argued that there should be no mistake, or the fixed point condition should hold for all neurons for memory pattern number 1. But if I make a stronger requirement that it should also be true for neuron pattern number 2, 3, 4, 5, until P. What would be the condition? I'll give you the answer. So this is the condition for no mistakes for existence of a fixed point for a single for memory with a high probability for memory pattern number 1. The condition for fixed point for all memory patterns with high probability is P smaller than n divided by 4 log n. Turns out that this is it's a nice exercise, and those of you who feel that this was somewhat difficult and are not sure that they were able to follow all the steps are encouraged to repeat this calculation for the case of when the requirement is no mistake, sorry, the existence of a fixed point for all neurons for all patterns. Questions about that? I think that these are good news. What it tells us is that in large cortical networks, where we know that the number of neurons is large, the number of patterns that at least can serve as fixed points in this model is large. So let's say that our n is 10 to the I don't know, 10 to the 7. So the condition would be that P has to be smaller than 10 to the 7 divided by 2 log n. What's log of 10 to the 7? Good, which is equal to maybe 20, approximately 20. So the requirement, the number of patterns that can be stored would be 10 to the 7 divided by 40, something like this, which is a large number. Actually, the requirement that we had here is rather restrictive. We wanted that the fixed point condition would hold for all neurons, and we were not willing to tolerate even a single mistake with a high probability. Single case, a single neuron that will not obey the fixed point condition. And we can make we can make a weaker requirement and say something like, well, maybe we don't need that all neurons, that the fixed point condition would work for all neurons. How about that 99, it will work for 99% of the neurons? What would be the requirement then? And another way of thinking about it is to ask a question. Let's say that we increase the number of patterns we embed in the network beyond this limit. What would happen? So it turns out that initially nothing much happens. So we will have some, looking at the dynamics of such networks, at the beginning nothing much happens. And the fixed points of the dynamics are almost the memory patterns, are very close to the memory patterns. But the problem is that if the fixed point condition does not hold for one neuron, then it will change its state. If it changes its state, it changes the local field for all the other neurons. It changes the input to all other neurons. So even if initially they were if initially the fixed point condition held, then after a particular neuron change its state, another neuron may, as a result, change also it states the fixed point condition position neuron may also not hold, and this may result in an avalanche ending in catastrophic consequences. So it turns out that as long as a P as long as the number of memory patterns is smaller than some number, something like 0.13 something, 138 something, as long as the number of patterns is smaller than this number, then we don't have this avalanche. Then we have the dynamics of the network converges to memory patterns that are almost, or to states which are almost the memory patterns. But if we go beyond this number, there is a total collapse. Physicists would call it a first-order phase transition, resulting in fixed points that have nothing to do with the memory patterns. The exact details, the exact numbers here are, of course, a property of the particular details of the model that we used. More generally, we can say that these networks have a capacity to store a very large number of patterns, number that is proportional to the number of neurons in the network. And again, thinking about cortical networks, maybe 10 to the 6, maybe 10 to the 7 neurons, then in principle, these networks, turns out that these networks have a capacity to store approximately that number of different memory patterns. So far, we only spoke about existence of a fixed point. Turns out that these are also stable fixed points. So far, we only spoke about the simplified case where beta was approximately, or we took the limit of beta goes to infinity. What we're going to do now is study the effect of beta on the dynamics. Any questions about the case of beta goes to infinity? So more or less we understand the case of beta goes to infinity. Now we are interested in the general case. But it's always useful to think about limits when studying a model. So we understand now the limit of beta goes to infinity. Now my question is, what happens as beta goes to 0, in the limit of beta goes to 0? What do you think would happen? So the way that we will, this will be easy. The case of beta goes to 0 will be easy, and we will do it, we will study it using the energy function that we defined a few weeks ago. So as you remember, we wrote down an energy function that had this shape. It was equal to -1/2 sum over I and j, Jij, Si, Sj, minus sum over I of Hi0, Si, plus sum over I of G of Si, where G of Si was this integral of g to the minus 1 si prime ds prime. You remember this energy function, this Lyapunov function? And what we proved was that the fixed points of the dynamics, we proved that the fixed points of the dynamics are minima of this energy function. And we will use this result in order to study the case where beta goes to 0. Now, this is easy. These two terms are easy. The term that is less intuitive is this sum over I of g of si. And what we will do now, we will go back to this term and try and understand it and see how it contributes to the dynamics, and how this contribution depends on the value of beta. So let's look at g of x. This, so g of x is hyperbolic tangent of beta x. So this goes from minus 1 to 1. This is g of x. This is x. This is 1, minus 1, and 0. Right? This is g of x. G of minus 1x is simply minus 1. This is plus 1. Function that looks something like this. This is g. This is x. G to the minus 1 of x. And the third function that we need to, now we need to look at the integral of this function. So this would be g of x be minus 1. This would be 1. So as long as we integrate g to the minus 1 in the negative part of x in the integration, g goes down because g to the minus 1 is negative. And from this point, as we integrate more, we have a positive contribution, and the shape of the function is something like this. Questions about this? So what's the role of this function in the when thinking about this energy function? Let's go back to this energy function and try and understand the minima of this energy function. So there are three terms. What about this term? Let's start with this term. When would this term be smallest? This is an external input. We're going back to the equation that we had for general symmetrical networks. So we proved that the dynamics of networks converge to minima of this energy function. So I'm going back to this equation. I'm trying to understand it, to think about it again. So when would this term be minimal? So when HI is positive, SI should be as large as possible. When HI is negative, SI should be as negative as possible. So this is the response of the network, or the response of the neuron to the external input. What about this term? This term is an interesting term. This term is tells us how the connectivity matrix of the network shapes the activities, in the sense that if two neurons are connected with positive connections, they should have the same sign, and they should be as large as possible. If the connectivity between two neurons is negative, then these terms should be, then the sign of this term should be opposite to the sign of this term, and the absolute value should be as large as possible. So note that here, the terms here, if we only had these terms here, then the values of S would go to plus or minus infinity. This would be this would minimize this term here. So what does this function do? So this function restricts, this function G restricts the values of the S of the activities such that they will not go beyond -1 and 1. Now the exact shape of this function depends on the exact shape of this G, which depends on the value of the beta parameter. So what happens when beta goes to infinity? How would this function look like when beta goes to infinity? God forbids parabola. When beta goes to infinity, hyperbolic tangent becomes a sine function. This is when beta goes to infinity.
Sorry, what happens when beta goes to 0?
We will talk about beta goes to 0 in a second. So if this is a sine function, this becomes how would you call this function? Well, this function becomes this function, okay? Now the integral of this function is this function. Basically, what it tells us that when beta goes to infinity, this G function doesn't care as long as S is smaller than plus or minus 1. So basically what this term, the contribution of this term is, I don't care what the values of the S's are as long as they don't go beyond plus or minus 1. Since these terms these terms predict that SI should be as large as possible, when beta goes to infinity, the fixed points would be plus and minus 1 because of this function. So these push the activities of the neurons as far away as possible from 0, either to the direction of plus infinity or to the direction of minus infinity, and this function G stops them at plus or minus 1. Okay, so this was a case of beta which goes to infinity. What happens in the case that we're studying now, that beta goes to 0? What would happen when beta goes to 0? Let's do it in in a formal way. So when beta goes to 0, the g function, hyperbolic tangent, goes to what? We don't take beta to be equal exactly to 0 because then it's boring. We take the limit. We take beta, which is small. So what's the Taylor expansion of beta x? So this would be g of x. So what is g to the minus 1 x? One over beta x. Why is it true? G of g to the minus 1 of x has to be equal to x, right? Are you with me? Okay. So what's g of x? Well, you can't see anything here, I guess. What's g of x? That would be the integral, right? Which would be equal to integral of this 1 over 2 beta x squared. So in the limit that beta goes to 0, this function, as you said, becomes a parabola. So what does it tell us? What does it tell us about the fixed points if this g of x is a parabola? I'm sorry? You have to commit yourself to an answer. You started by saying there aren't any, and now you say that it's 0. Why did what?
G limits what if I, how big is I or how small is I?
Right.
And the parabola,
Why isn't it limited?
can go beyond 1. I mean,
Okay.
before we had an asymptote and 1 and minus 1.
Well, first we know that it will not go beyond 1 and minus 1. Because, remember, this is just a Taylor expansion of the hyperbolic tangent. So it cannot go beyond 1 and minus 1. The dynamics cannot go beyond 1 and minus 1 no matter what. If we have this result that it goes beyond 1 and minus 1, then it means that we have a mistake. But the way to think about it is the following. This equation is this is a quadratic equation SI and SJ. This is linear. This is a quadratic term, a linear term, and here we'll have a quadratic term. And actually, this quadratic term will dominate because in the limit of beta goes to 0, this would dominate the quadratic term. So basically, what we have here is a paraboloid. It's like a parabola, but a multidimensional parabola. And we know that the paraboloid has how many minima? 1 minimum. So we know that as beta goes to 0, the energy landscape becomes a paraboloid. So the dynamics has just a single fixed point, and it will converge to this single fixed point. So that now it's interesting, because we know in one limit that we studied, limit of beta goes to infinity, there could be many fixed points, p fixed points. Maybe there are more. We will discuss it. There are many fixed points, and all these different fixed points somehow disappear, except for one, leaving us with a single fixed point in the limit of beta goes to 0. So something interesting happens as we go from beta, which goes to infinity, to beta that goes to 0. We understand the two limits. We understand beta goes to infinity. We understand beta goes to 0. And what we will do, I think, after the break, would be to study the general case of, well, just have a glimpse of the general case of beta, which is not equal to 0 and not equal to infinity. Intermediate values of beta. Any questions? So let's take a break.
היו 4 סימנים שונים של P ואני מתנצל. היה ככה, יש P,
זה בסדר, מבחינה התנאי הזה, אבל זה הסתברות.
זה הסתברות לטעות בין לפחות אחד לנוירון.
מה שכתבת. עכשיו כשכתבת אלפא שזה T חלקי.
זה הגדרתי אלפא.
מי זה הכי הזה?
זה הכי גדול, מספר הפאטרים. לפי קפסול P זה מספר הפאטרים.
כן, קיבלנו מספר הפאטרן. מספר הנקודות היציבות שכל הנקודות לא יצאו.
שסידרתי כבר את כל העברית במחשב שלי, אז גם כשאני באנגלית, אז אני לא יודע מה זה אומר, אבל כל מה שכתוב באנגלית אפשר לקרוא בכל מידה.
כן. פשוט כאילו כשאתה רוצה להתחיל להחליף שלוחה.
זהו, אז אני עושה, פשוט אני עושה שלושית כמו שכולם עושים. וככה אני פותח לאנגלית. מה?
נראה לי שאתה על זה.
זהו, אז ככה זה כותב באנגלית. ואני אמרתי שבעברית זה לא עובד, אז התחלתי לאנגלית, ואז הוא רוצה לעשות אקספורט לאנגלית, והוא עדיין עושה את הבעיות, והוא עושה את זה בעוד יום אחרון. כי אני שולח את זה לעצמו, וצריך פשוט להחליט את זה בחזרה, וגם ככה תהיה את זה. אבל אם אני אתחיל מראש ואני אקרא חובה, אני בבית אבל נכון. למה שאני אגיד כאילו מאחורי המאחורי משתגע על זה כל זה.
אז זה בטח יש לך יש אחד שמעביר מדינת וילוס.
לא, הוא שכולם מכירים, שמסתובב בכל מקום. לא.
אני לא
יש לי חברים שהם עושים הכל ביחד. זה ממש הכל בעברית. כל אחד מהם
בזמנו מישהו שלח לי, כאילו, גם אני כזה לא כל כך רגילים בעברית. בזמנו מישהו שלח לי פשוט איזה אתר שמסביר איך להתקיל את זה טוב, והתקלתי וזה עבד.
זהו, אז אני גם, יש כמה כאלה, כולם כותבים אותו דבר. להתקיל וגם אחר כך להתחיל לקצר את הפלוגין הסתדר. עשיתי את זה.
וזה לא עבד?
ועדיין, אני רוצה אקספורט ולא מקבל את זה. והתקנתי את המיקסקס, והתקנתי כל מה שיכולתי,
יש, אני חושב, כי אני לא כזה מהמלחכים, אבל יש איזה מין אתר כזה שכאילו כל העבודה אצלי אונליין. אז אין שם בכלל עניינים של כזה להתקין פלאגינים עוברים מחשב למחשב, זה כאילו הכל כאילו וובי. אז אתה יכול לעשות את כל הצורות.
זה אותו...
זה כאילו זה לטקס, זה אותו סינטקס. זה עובד באנגלית, הם כאילו טענו שזה גם עובד בעברית, וניסיתי, וכאילו עכשיו הם עשו איזה עדכון שכאילו גם בעברית להפסיק לעבוד, אז כאילו שלחתי להם מייל ושכאילו שישחררו את זה. ולא יודע, נראה ממש סבבה.
זה טוב?
זה נקרא אולי share latte קוראים לזה, אני יכול לראות שזה טוב.
כן? אני אשלח לך מייל, תשלח לי קישור? חשבתי שם. פשוט תחפש בגוגל share latte.
אני לא בטוח שזה השאלה, אני אסתכל שנייה. וזה כאילו לא ממש עבדתי עם זה, אבל זה נראה לי אחלה. זה באמת כזה, אתה יודע. באופן כזה אני לא כזה אוהב כזה לשמור קבצים על מחשב שלי, להתחיל לשלוח וללכת לאדוב וכו', הכל שם.
באמת.
אז זה הכיוון.
זה משהו שהולך לשם. אבל עדיין, כאילו, עדיין יש את הערך של דברים שנמצאים לך על המחשב לוקאלית בקטע של, כאילו, גם זמן מסע, גם תלות בחיבור לעמותות, וגם כאילו מסיבות שאתה מעדיף כאילו לדעת איך אתה מאבטח את הדברים שלך, שהם ישמרו אצלך במקום כאילו...
למרות שגוגל ומאבטחים את זה לא יצטרכו שכל אחד יכול לפתח.
ברור. מצד שני גם אם מקבלים צו מארצות הברית לתת להם אוטומטית את כל הזה, או שיש איזה backdoor או הנערף, כאילו.
100%.
אין לך יודעים הכל.
אני הייתי משער, הייתי נכנס לשם עם טנקים, משהו שדומה. שנים מה גוגל יודעים לעשות, איזה פונקציות חוצים.
אני יודעת.
זה לא חוצים את הבן אדם. זה מה שקוראים לזה. משהו של, מה שקוראים לו information mining. ברגע שעכשיו אתה עובר, שלא חייבת שזונות משרתים זרים,
הבעיה של NSA זה לא שחסר להם מידע, הבעיה של NSA זה לא שחסר להם מידע, זה שיש להם יותר מדי מידע. אתה יכול להתמודד עם דבר כזה. לא, אתה צריך לעשות כל מיני... אבל תמיד עם החילונים האלה יש
אוקיי. So the Hopfield model turns out to be a rather interesting model. We studied, we started to understand it in the limit of beta goes to infinity, and we saw that as long as we don't encode too many patterns, then the patterns that we encode are fixed points of the dynamics. It can be proven that there are stable fixed points of the dynamics. We will not prove it. One interesting result, I leave it to you as an exercise to see that not only the patterns themselves are fixed points, but also minus the pattern, minus the memory pattern, is a fixed point of the dynamics. So minus p mu, the vector minus p mu is also a fixed point of the dynamics. Then we talked about the other extreme case where beta goes to 0, and then we know that there's only one fixed point. The dynamics is only one fixed point, so definitely the system cannot store any memories. And what we will do now, we will study becomes a rather perhaps a semantic question of whether a system that has is it a memory pattern? Well, okay, so let's see. Independently of the initial conditions, you always go back to the same thing. So independently of what I tell you, you always think about just one thing, okay? And this thing has very little to do with and this minimum is not very close to the pattern that I tried to encode in your brain, right? So it's both one minimum that has little to do with the pattern that was were encoded in your brain. So it's not well. I don't know. You can, if you want to call it one memory, fine. I don't know. I think that less than one. Well, one memory is not very. The system has to be multi-stable in order for you to be able to say that it remembers something. That's the way that I think about it. But this is semantics. It's not not very important. Yes.
I have a question about the minus pattern also being
Yes.
So say I take the number of memories I want as pretty much the maximum that the network can have, like
Okay.
0.14 tangent.
Okay.
But then also the minus patterns are stable, so I have twice that many.
Oh, the question was not about the number of. The question was not about the number of fixed points. The discussion was not about the number of fixed points. The discussion was about the number of patterns that serve as fixed points of the dynamics. So what happens is that when you further increase the number of patterns that you encode into the system, the number of fixed points does not decrease. You still have many fixed points, but they have nothing to do with a pattern that you encoded in the system. As we said a month ago, it's rather easy to have to construct a network that has a large number of fixed points. What we want is that these fixed points would be interesting fixed points, useful fixed points.
No, but I mean, that means that.
It means that you have, let's say that you take a Hopfield model with a single memory pattern. It means that this dynamics, well, we didn't see it, we will see it now, has two fixed points. And when you encode 7 memory patterns, you have, actually you don't have even 14 fixed points, you have many more. And we will talk about it hopefully today, and if not, that would be the topic next week.
Are there any other
Yes. Yes. We will see one example today. Okay. So let's remind ourselves about the equations that we're using. So SI dot is equal to minus SI plus hyperbolic tangent of beta sum over J, Jij, Fj. So these are the dynamic equations. And now I'm going to define something that I'm going to call an overlap parameter. The overlap parameter is a parameter that tells me how similar is the network activity, how similar is it to a particular memory pattern. So the overlap parameter with memory pattern mu is just equal to 1 over n sum over I of pi mu Si. So I have the state of the network is a vector of activities Si, I goes from 1 to n, and the overlap parameter is the sum of the product of the network of the activities of the neurons with the memory patterns. For example, what would be the overlap parameter in the case of that the network activity is equal to the memory pattern? 1. To gain insight, well, let's see why this memory, why this overlap parameter is useful. Is just consider this term sum over J of Jij Sj. This is equal to sum over mu pi mu pj mu one over n sum over J. So pi mu 1 over n sum over J pj mu Sj. Right? What I did here was to write Jij as sum over mu of 1 over n pi mu pj mu. What is this term? It's the overlap of the state of the network with the memory pattern mu. So this is equal to sum over mu pi mu m mu. So the input of the input to a neuron, this term can be thought of as a linear, or is equal to a linear combination of the overlap of the network with the different memory patterns. Yes. Yes, you're absolutely right. We have JII is 0, and as a result, I'm missing one component in the sum. So this would actually be equal to pi mu mu minus something, which is actually equal to, it will be m, but the question is how large is this contribution that I'm missing? What's the magnitude of this term that I'm missing here? It will be one term, right? So this would be a 1 over n correction. So we don't care much about it, but formally you're absolutely right. Let's look now at the dynamics. At the dynamics of this memory pattern, of this overlap parameter. So m mu dot is equal to 1 over n sum over I of pi mu times si dot, right? Which is equal to 1 over n sum over I of pi mu times minus si plus hyperbolic tangent of beta sum over mu of pi mu m mu. Which is equal to, what's the first term? Which is equal to minus mu plus sum over I, 1 over n sum over I of pi mu hyperbolic tangent of beta sum over mu pi mu m mu. To avoid, this is a rather confusing notation because this is a different sum. This is not the same mu. Mu is just an index here. To avoid confusion, it's better to use a different letter, like mu prime. To gain insight, let's consider the case where there's just one memory pattern. We'll remember this. We'll remember this equation. This is a general equation. And consider the case of a single memory pattern. So if you only have a single memory pattern, then mu, in principle, we can write p equations, one for every memory pattern. But if we only have a single memory pattern, then we have just one equation. So this would be m1 dot is equal to minus m1 plus one over n sum over I pi1 hyperbolic tangent of beta pi1 m1. Right? Questions? What's the next step? Or we can do. There's a trick that we can use. pi1 is plus or minus 1. So hyperbolic tangent. So if it's plus 1, then we can just throw these two away. If this is minus 1, then this would be minus, but we'll have here minus 1. As someone said here, hyperbolic tangent is an odd function. So this is just equal to minus m1 plus 1 over n sum over I of hyperbolic tangent of, what's pi squared? 1. What's the next step? What is this? What's this sum equal to? It's 1 over n, sum of n terms, which are all exactly identical. And what's the solution? What's the solution? What's the fixed point solution? Who said 0? Well, if it is 0, how come that we were able to store memories previously in the case of beta goes to infinity? I'm sorry?
Depends whether the beta is smaller or larger than 1. Because you need to
So the fixed point solution is M1 is equal to a hyperbolic tangent of beta M1. And now we need to ask the question of whether this equation has a solution. What are the solutions? I think we did it, right? We did it at least once. We found the solutions of this equation. So what are the solutions of this equation? So one possibility is that M1 is equal to 0, or M1 is equal to plus minus M star, which is not equal to 0. And we have such a solution when beta is larger than 1. And in the limit of beta goes to infinity, this solution goes to plus minus 1. We did it in the past. But now we can ask a question that you asked me several times about the stability of the fixed point solution, because now we have equations. We have dynamical equations. So how do we compute the stability? How do we compute stability here? Small perturbation and... I'm sorry? Okay. So how do we do that? Delta M1. Linearize around the fixed point. And I think we did it in the previous version, right? So how does the stability matrix here look like? We did it in before Pesach for the case of one neuron with self-coupling. So I will not do it here. But basically, what we find is that this solution is stable when beta is smaller than 1, and this solution is stable when beta is larger than 1. Okay. So this was a rather simple case, because this was an example where we encoded only a single memory pattern in our network. Obviously, we are interested in more complicated cases where we embed multiple memory patterns in our network, and so that's what we will do now. But it's rather complicated. It's rather complicated to solve the most general case. So we will restrict our case to we will consider a simplified example where the number of patterns is 3. There are 3 memory patterns. We encode 3 memory patterns. So this would be a case where Jij is equal to 1 over n sum over mu pi mu pj mu. So now we have 3 equations, right? We have 3 equations for So now we need to decide what to do with this equation. Let's write it for M1. M1 dot is equal to M1 minus M1 plus 1 over n sum over I of pi1 hyperbolic tangent of beta times pi1 m1 plus pi2 m2 plus pi3 m3. So this is one equation. This is equation for M1 dot, for the overlap with memory pattern 1. There will be another equation for memory pattern 2, and the third equation for memory pattern 3. Now we can no longer use the trick that we used previously to take in this simple case. So what do we do? Let's look at this term. Well, this is easy, right? We don't need to worry about this one. But this is complicated. Why is it complicated? We have n terms here. We need to worry about n terms. Now, is it really the case that we need to worry about n terms? I'd like to argue that, in fact, we need to worry about a substantially smaller number of terms here. What are the stochastic variables here? P. This is one stochastic variable. This is another stochastic variable, and this is a third stochastic variable. We have the same stochastic variable here. So these numbers, the pi1, pi2, and pi3 are all terms, are all variables which are equal to either +1 or -1. Why does it help us? There are only how many? Well, this one is the same as this one. So we have a sum of n terms. We have a sum of n terms. But these n terms can be one of 8 possibilities. It could be that all 3 pi's are +1. And how many how many such cases will we have? 1/8. 1/8. We have 1/8. Exactly 1/8. approximately 1/8. Why would it be one? Why did you use a number 8, not 1/7? Okay, so each of these patterns can be plus or minus 1 with a probability half. So the probability that all three will be plus 1 is 1/8. But this does not mean that 1/8 of the cases would be with the probability, would be 1/1/1, right? Well, because it's a stochastic number. It's expected value. The expected value here. So what I'm going to do, I'm going to replace this term with its expected value. I'm going to replace this term with its expected value. So I'm going to write it down, and then we will justify it. Just a second. So I'm going to argue that this equation, where I have a sum over n terms, will behave approximately like this equation, where I replace this term with its average over realizations. And in a second, we will open this term and see, and we will write it explicitly. Now, the question is, why is it justified? Or do you want to ask me a question first?
Why would not we approximate it to a Gaussian with a very larger net?
Actually, this is what we are doing.
Why not do it now and have a super equation?
Well, it will not be a simpler equation. So what we will have here is different realizations, different networks, different memory patterns will result in slightly different dynamics. Because in one case it will be 1/8, the 1/1/1 will be 1/8 of the case, and in some cases it will be 1/8 of the cases plus something or minus something. And the question, how large is this something? And the deviation from the expected value will be of the order 1/square root of n. As n goes to infinity, the deviations would go to 0. So that's why it is justified to replace this with the average. And now you can ask me, why didn't we do it before? In the case where we studied the case of beta goes to infinity, we did care about the fluctuations, and here we don't. Why did we care about the fluctuation in that case, and we don't care about them here? In the previous hour, we studied the case of beta goes to infinity. We had an equation. Well, we had a fixed point equation. We don't have the dynamics, but then we cared both about the mean of an equation that has this flavor and about the standard deviation. And here I'm saying, yeah, we don't care about the standard deviation. It goes like 1/square root of n. Why is it justified here and it was not justified there? What's the difference?
There are small changes from 0 that cause large changes in the sign function. Small change in x.
Not what we are doing here. I'm arguing that we can replace this function by its average over the realizations. But previously, we also took into account the fluctuations. So now the question is, why did we have to take into account fluctuations previously, and we don't take them into account here?
Previously, the deviations caused, that's what controlled the probability.
Well, maybe they also control it here.
But there the average was 0,
No, the average was 1. 1 plus, it was 1 plus fluctuations.
But the average of Z there was 0. So we had to take the second, we had to take the fluctuations into account.
What was the size of the fluctuations there?
Because beta was in
It was P over N. The variance was P over N. And the standard deviation was square root of P over N. And what's going on here? P is small, exactly. Here P is equal to 3. So if P is equal to 3, then the fluctuations are order of 1 over square root of N. This was also true in the previous case. If we would have taken P, which is equal to 3, we would not have cared about the fluctuations. There, we were interested in large P. Actually, we cared about P, that is order of N, or maybe N divided by log N, a large P. Here we only care about P, which is equal to 3, and there, as a result, the fluctuations are order 1 over square root of N, and we don't care about them. If we would solve this, if we write down this equation, not just for 3 memory patterns, but for a very large number of memory patterns, so we'll have a very large sum here, then we would start caring about fluctuations. Is it clear? Is this point clear? Okay. So what do we do next? What's the meaning of this average, actually? What's the meaning of this average? The meaning is that we take all possible we replace this sum with its expectation value. So how many terms would we have here? How many different situations do we have here? 8. So what are these 8? So let's write them explicitly. So we have m1 dot is equal to minus m1 plus the first possibility. Well, what's the probability of each of them? The probability is 1/8. And now we can start writing them down. We have this would be hyperbolic tangent of beta times. What would be the value for 1, 1, 1? This would be just m1 plus m2 plus m3. אולי נחכה עד סוף השיעור. What would be the second term? This term? Well, I'm checking all 8 possibilities. Now I consider the possibility of 1, 1, 1. So for 1, 1, 1, this contribution here was 1. What's the second possibility? What would be a second term? Well, let's consider 1, 1 minus 1. So 1, 1 minus 1 would contribute hyperbolic tangent of beta m1 plus m2 minus m3. This would be the case of 1, 1 minus 1. And we will have the case of 1 minus 1, 1. So this would be plus hyperbolic tangents of beta m1 minus m2 plus m3. And we'll have the case of minus 1 minus 1 minus 1. So this would be hyperbolic tangent of beta m1 minus m2 minus m3. Is it clear to everyone what I'm doing here? So these are just 4 terms. And what would be the next term? Well, the case of P1, which is equal to -1. So this would be minus hyperbolic tangent of beta minus M1 plus M2 plus M3 minus hyperbolic tangent of beta minus M1 plus M2 minus M3. And we have 2 terms to go, minus hyperbolic tangent beta minus M1 minus M2 plus M3, and the 4th term, which is hyperbolic tangent of beta minus M1 minus M2 minus M3. So I have good news and bad news. The good news is that we replaced a horrible sum over n elements, maybe 10 to the 6, 10 to the 7, with this sum over 8 terms. It's slightly more complicated because this is just for M1 dot. We'll have equation for M2 dot and an equation for M3 dot. But still, 3 equations with 3 variables. This is something that we can handle, and if you look carefully, you find out that actually we can simplify this equation. Yes. Because we have P both here and here. So we are computing the expectation value of this term. But it's an expectation of a function. You cannot replace an expectation of a function with a function of expectation. But it's also here. Life is hard. It's not as bad. I mean, look at this term. This term is equal to this term. And this term is equal to this term. And, well, basically we have 4 terms here. You can simplify by a little bit. This was easy for me. Okay, so we have this equation for M1. We have this equation for M2, or well, an equation of a similar flavor for M2, an equation of a similar flavor for M3. And the only thing that is left for us to do is to find the fixed points of these equations and compute the stability. And this is what we will do next week. I was hoping to do it the last hour, but I guess that you will have to wait. Any questions? So the plan for next week is to finish this calculation and talk a little bit about the relation, going back to the limits of the Hopfield model and relation to biology, and then move to a different kind of memory model. תודה רבה.
קודם זה היה מקרה שבו אנחנו עשינו אנקודינג של תבנית זיכרון. עכשיו עשינו אנקודינג של 3 דקות. זה מקרה, אתה יודע, מקרה אחר. נכנסתי, המטריצה G.I.J.
בעצם בכל הרעיון האחרון שתגיד מלא, לא מבזבזים מלא משאבים, יש לך שום השלכה שרוצה לבחור תמונה, יש לך מלא פוינט, שכל שומעים אותה תמונה.
לא רוצה לשמור, אני רוצה כל מיני דברים, קודם כל אני לא רוצה לשמור תמונה אחת, אני רוצה לשמור הרבה תמונות.
אוקיי, נניח, תמונה אחת, איזשהו מיוט.
אני רוצה לזכור אבל התמונה עצמה. לא רוצה סתם לדעת שאני עכשיו התמונה הזאת. אני רוצה שהתבנית הפעילות של הנוירונים, בזמן שאני מדמיין את התמונה הזאת, תהיה דומה לתבנית הזיכרון בזמן שאני רואה את התמונה. זה מה שאני מקבל.
אבל מה שהראינו עכשיו, שבשביל איזשהו מצב מיוט, בשביל איזשהו מספר גדול של פיקסים שכולם כאילו בסדר, מגיעים את התמונה.
לא את אותה תמונה, כל תבנית זיכרון יש את הפיקספוינט שלה.
לא ברור לי אז מה ההבדל בין
וקטור P זה תבנית הזיכרון שאני רוצה לשמור במערכת. אני מכניס עכשיו באיזושהי צורה משנה את התבנית הזיכרון דרך לקבל משהו. קיבלתי את זה. עכשיו, התבנית שקיבלתי יש כאן את הבחנה הזאת, שאם אני מתחיל בתבנית זיכרון שהרשת, תבנית הזיכרון הראשונה היא פיקספוינט שלה, תבנית הזיכרון השנייה היא גם כן פיקספוינט שלה, תבנית הזיכרון השלישית היא גם כן פיקספוינט שלה. לא, תבנית הזיכרון זה 3 תבניות זיכרון שונות, כל אחת מהן פיקספוינט, שבתוך הפיקספוינט של הרשת, התמונות הן פיקספוינט. תבניות התמונה הן
זה 3 תמונות?
הרשת יכולה להיות נגיד שהכנסתי 3 תמונות לרשת. נניח ש-G.I.J. מורכב מ3 תבניות. כל אחת מתבניות הזיכרון שונות, כל אחת מהממורי פאטרן הוא פיקספוינט של הדינמיקה. כל אחד הוא פיקספוינט של הדינמיקה. הראשון, המשמעות הקוגניטיבית שלו זה שאתה זוכר את א', השני, המשמעות הקוגניטיבית שלו זה שאתה זוכר את ב'.
זה לא המיועים השונים? זה מיועים.
מיועים זה האינדקסים של תבניות הזיכרון. יש לי רשת של F, לפעילות הנוירונים. יש לי איזשהו קונספט אבסטרקטי, זה ה-P של תבניות הזיכרון. מה שהייתי עושה זה רשת שמתכנסת, ה-F'ים אליהם מתכנסת, זה או P1, או וקטור P1, או וקטור P2, או וקטור P3. זה מה שאני עושה.
אני אומר, זה שיש עכשיו באיזושהי גם
P1 מייצג תמונה אחת, להיזכר בתמונה אחת. P2 זה תמונה אחרת.
כל תמונה יש לך P1?
כל תמונה יש לה וקטור P.
P משלו יחיד.
בדיוק.
יש לי עוד שאלה קצרה. תסתכל על ה-G גדולה, אין איזה משמעות לקבוע, כי אתה בוחר אותו אפס.
לא, אין משמעות לקבוע, זה בוחר אותו מה שאתה רוצה.
למה?
מעניין שזה המינימום של האנרגיה.
אז שוב, בוחר אותו אפס.
השאלה היא תמיד מה אתה מה התופעה הביולוגית שאתה רוצה למדל.
כאילו, אני מעניחה את הגיל
שם יש אלטרנטיבות, לא כאלה מלהיבות. דבר על מודלים אחרים, כל מיני דברים אחרים. זה לא, הקורס לא נגמר כאן.
באמת? זה גם לא?
היי.
I was wondering if you maybe have an idea of the time where we could sit down and discuss. I'm gonna make it through the semester.
לא הבנתי אם ניסה להגיד שאנחנו צריכים להיות נורא מפורטים, והיא לא מפתח את עצמה, או
Next Wednesday,
ובאחד מהם יש כנראה איזשהו
זה לא משהו אני חושבת שמתכוונת כאילו אל תעשו כזה, אל תדברו בהיי לבל.
in my office downstairs.
מה אחד השאלה הראשונה? אני יכולה התחלתי לקרוא את המאמרים שלי, דווקא, לא, הוא ממש קריא את נחמד, לא... כן, זה ממש, לי הוא נחמד גם כי אני לא יודעת כלום על זה, אני לא יודעת, זה תלוי באיזה קיצור יעלה לי בשביל לדעת שכזה משהו זה או לא.
אבל כאילו הוא גם משפיע על הפלטפורם, נכון? זה משפיע על ה-DXC?
לא, AI. כי הוא משפיע כמה רחוק זה יגיע, לא?
הוא גם משפיע על הפלטפורם, נכון?
הוא משפיע על הפלטפורם, איזה?
האקטיביטי, הנוח שהוא יותר מקום.
כן, אני חושב, יש שם...
כי הוא גדל את כאילו הקוואדרט הזה, אז הלוג משתנה מיקום, הוא יותר גדול יותר קטן. כאילו...
טוב, אולי אתם קראתם זה בנאטלס.
שם סטטיסטי, אני סדרתי את זה, כאילו שלא ש...
אבל זהו, אני חושב שלא תערכים.
כן, אני מאוד להגיד בו. אבל מטריק,
אז נכון, מה שקורה זה שכאילו... זה אנחנו לומדים.
לא, אבל בתרגילים יש מעט מאוד טיעונים אנליטיים.
אחד התרגיל הרבה לפני שאני
אני חושבת שזה יותר קשה מהנבחן, זה לא ככה גם שבירות, נראה לי.
אבל התרגיל לא דורש באמת להבין את החומר עד השלב שבו צריך להסיר מהסך, ואז... כאילו, אני נגיד תמיד עושה תרגיל, באמת בלי שהבנתי כלום, לא כלום, אבל בלי שהבנתי הרבה, ורק בסוף אני חוזרת להמציא את ההסבר כזה ומסתכלת על מה היה בשיעור. להזכיר את התרגיל? אני יכולה להסביר גם כאן.
נגיד, מה שיפה עכשיו אני ממש מקווה שלא נצטרך לעשות את זה.
וואי, יש שם כמה שלבים שאני לא כל כך יודעת מה לעשות. כן, צריך לעבור על השיעורים האלה.
לא, שיעור עכשיו נראה לי שהיה שיעור
הכי קשה, זה כבר גם בעיה. כן? אני לא יודעת אם זה הכי גרוע, זה היה גרוע. שצריך לעבור, רק שהוא באמת כל כאילו...
ממש לא חושב.
לא, צריך להבין, אני מבינה, כאילו מה, אני שאלתי את כל הזמן. אני לא אשתכנע שבהצלחות צריך לעשות את זה כמה שנים בשביל להשתכנע, אבל לפחות שאני מבין מה הוא עושה, כי אני מסתכל
טלפון. סבבה, אבל אתם לא אומרים כלום היום. זהו, כן, לא,